Picture this, you're organizing a party and you need to figure out the best combination of friends to invite based on their interests. It sounds straightforward, but what if you had to consider every possible combination? That's exactly the challenge we are facing today, a problem from HackerRank. We'll explore how to work with subset and components in a way that's not just theoretical but also applicable to real life situations. Curious about how to break down complex combination? Stick around. Alright, let's dive into the problem we are tackling today, the challenge of finding connected components and in subsets of an integer. Now, at first glance, this might seem like just another coding challenge, but what's really fascinating is how we bring together concepts from graph theory and bit manipulation. So let's break this down step by step. First, we need to understand what we mean by connected components. In graph theory, a connected component is essentially a subset of a graph where any two vertices are connected to each other by paths and which is not connected to any other additional vertices in the supergraph. In our case, the integer from our input can be thought as a vertices in a graph. And now imagine we have a set of integers and we want to look at all possible subsets of these integers. Each subset forms its own graph, but not every subset will be connected. Our goal to find how many connected components exist within each of these subsets. So how do we approach this? Here's where a magic of bit manipulation comes into play. Every integer can be represented in binary form where each bit can either be 0 or a 1. When we talk about combining integers using bitwise operations like OR, we can efficiently track which bits are set, which in turn tells us which integers are part of the subset. Now let's break down our strategy into clear steps. Number 1, generate all subsets. The first step is to generate all possible subsets from the given sets of integer. We can use bit masking to represent these subsets efficiently. Each bit in a number can represent whether an integer is included in a subset or not. Number 2, combine integers. Once we have the subsets ready, we can combine the integers in that subset using the bitwise OR operation. This gives us a single representation where each bit can position correspond to whether that integer is included in the subset. Number 3, count set bits. After combining the integers, we need to count how many bits are set. This tells us how many integers are actually part of our subset. And number 4, find connected components with our combined representation so that we can now determine how many connected components exist. For each bit that is set, we check if there are any connections to other set bits. This is where depth first search or DFS comes into play. We'll explore from one set bit to see how many other sets we can reach, marking them as visited along the way. And number 5, aggregate results. Finally, we will repeat this process for every subset and integrate the results to get the total number of connected components across all subsets. Now that we have a clear game plan, generating subsets using bit masking is quite efficient as it allows us to iterate through all possible combinations without needing nested loops. And however, we need to keep an eye on the complexity of connected components, especially since we could potentially be dealing with many subsets. As we wrap, remember that understanding bitwise operation and DFS can be incredibly powerful tool in your coding toolkit. Whether you are tackling competitive programming challenge or working on complex algorithms, these concepts will serve you well. Check out the source code in the description below. If you have found this video helpful, don't forget to give us a thumbs up, subscribe and hit that notification bell. So stay tuned and as always, happy coding.